Welcome to the last but one lecture video. In this, I'm taking the divergence theorem. In the previous video, we took the Green's theorem and then the Stokes theorem, and I want to do a little recap of it. To use the Green's or the Stokes theorem, there are things we want to look at for. The first thing is that it would always provide itself in a 2D plane. The second thing is that the curve, is closed, simple, some positive orientation. And then the function f can be in a differential vector form or a vector field. And we established that if it's a differential form, you use a Green's theorem. If it's a vector form, you use a Stokes theorem. That means you're going to use the curl of f. Green's means the same double integral, but your second minus what? Your first. In all this, we are moving from a line integral to a double integral. Now, the divergence theorem, what are we looking at for? It mostly presents itself in a 3D plane. It means you have some x, y, z's. And then there also the curves is simple, closed, and positive oriented. Now, another thing to look at for is the description of your f. It's a vector field. One last thing is to check this keyword flux. Flux is the movement in and out of a medium. So if you should check these two things, you realize the difference here is the planes. 2D means you are moving to double. 3D means you are moving to triple. Another keyword is the use of the flux. Flux means divergence, movement in and out. I've explained that. So I'm looking at the divergence of my vector field. So divergence theorem says that move from a surface integral by the normal ds and then transform it into a triple integral using the div of the vector field. As simple as that. So the keywords I'm looking out for to use the divergence theorem, they should help you out. So let me take some few examples. In the first example, I have a solid Q which is bounded by some paraboloid. If I have to draw this intuitively, I'm having something like this. So this is in the 3D x, y, z. If I trace this up, it's as if I have another polar within. It is bounded by z and then some xy plane. So this is the z plane and then the xy plane. It says find the flux of the vector field. So I told you the keywords I'm looking at for. I see that my f is a vector field. Fine. I see the keyword flux. Immediately I see flux, I know divergence coming into play. And I check my plane. I have the z combining the xy, so it is 3. So in place of finding the work done over the surface, instead of finding this f and then the normal, I'm going to use the triple integral by just finding the div of f, and then my life is saved. So how do we find this? What is the div? My f is given as s cubed, y cubed, z cubed. The divergence, that is the dot product of f, it's going to be 3x squared plus 3y squared plus 3z squared. If I want to simplify this, I have 3 out. S squared plus y squared plus 3z squared. Now my z is given as, aside this, my z is given as 4 minus s squared minus y squared. Because it's 3 means that I need the my dA is something like dx, dy, dz. So I need to find a coordinate. If I set this to 4 into bracket s squared plus y squared, you realize I'm going to have 4 minus r squared. If I set this to 0, it means I have 4 minus r squared this. And then my r becomes plus or minus 2. Okay, so what can I do? If I do some substitutions here, you realize my first integral is 0 to 4 minus r squared for dz. My second is 0 to 2 for some dr. It means I need the theta. I'm moving to paraboloid which has a polar within. So it's like a cylindrical form. I need x, y, z will be transformed to r, theta, z. So what will be my theta here? That is 0 to what? 2 pi. Because of this radius here. You already know these things. Now the integrand, I found it to be 3 x squared plus y squared plus 3z squared. If I want to simplify this, I know x squared plus y squared is r squared plus 3z squared. Now my dA is r d dr d theta. So let me have that r dz dr d theta. But my triple still remaining here. If I bring 3 out, I'm going to have to just evaluate a simple 3 integrals of r plus 3 z. I've already found it, or I can just maintain my z squared. Any way you want to do it. Multiplying my r dz dr d theta. I have to just evaluate this simple. Instead of finding the surface integral where I need f and then the normal, you know the normal will become z respect to x all square plus z respect to y all square plus 1. And then my integrand will have to, that'll be a whole lot to do. I hope you've not forgotten your surface integral. So you can go back and then see how to solve surface integral and see the complexity it would be compared to just using your triple. That's your divergence theorem. If I move to a second example, it says we want to find the outward flux of a vector field. So I see a vector field, fine. I see a flux. Then divergence theorem comes to mind. It's over a unit cube. Cube is a 3D object. It's a 3D object, so I have my 3D in mind. I see my flux. This means triple, flux means divergence, and I have my vector field. So simply, it's a unit cube, so it means everything is 0 to 1, 0 to 1, 0 to 1, and then divergence of f dz dx dy, or dy dx dz, any way you want to find it. So let's see the divergence of that. This becomes, it's as if I have partial of x, in case you've forgotten. Dotting 2xi plus 3yj plus 2z square k. Then I'm simply going to have 2 plus, it is dotting, so 2 plus 3 plus 2z. I told you I dot I is equal to j dot j is equal to k dot k is equal to 1. So this is what I have to just work out. It means I'm simply finding the integrand as 5 plus 2z. These things can still be dy, dx, dy, dz because they have unit box. It's the same integrals. I have to solve simply this one. And that's the use of the divergence theorem. Let me see, I have a last example here. It says compute the surface integral of a vector over the radians. Fine, I see I have to compute some surface integral. I know the formula for a surface integral. It is f and then the normal unit. I have a vector field, but I see that the radians is given over 3 different boundaries or regions. So immediately I can use the divergence theorem. So it says find the div of my f, the A, and I'm done. So see, if I have a 0, 1, 0, 3, 0, 2, you know your dA will be what? The z, the y, the x. The divergence of f, it means I'll differentiate the first term respect to x plus the second term respect to y plus the third term respect to z. And that is all you have to do. So let me see if I can help you out here. 0 to 1, 0 to 3, 0 to 2. If I differentiate respect to x for the first time, I'm getting 3 plus respect to y gives me 2y plus respect to z, I get 0. This is a simple way of using the divergence theorem. So you don't forget the keywords in the problem you are solving to know when to use divergence theorem, when to use the Green's theorem, and when to use the Stokes theorem. And so this brings me to the end of my lecture videos on multivariate calculus under the unit vector calculus. I hope these videos have been helpful in the lectures we've had. Thank you and have a fruitful semester ahead.